Right. Thank you very much. And I'd also like to welcome you to the course, and in particular to the X-ray CT part. So I will be giving a short introduction to the core imaging library here today. Let me just share my screen. Here we go. I hope you see my slides. Is that okay? Good. Right, so we are a number of people involved, all associated to the CCPI network. Many of us used to be at the University of Manchester, and a lot of us are now, well, not me, but many are now at the STFC. So first of all, what is the core imaging library? So it's an open source, object-oriented Python framework for doing tomographic imaging mainly. At least that was the starting point. We can do other things than X-ray CT now. And I would say the focus is on, well, we can do standard X-ray CT, but our focus is really on being able to do challenging data sets. So X-ray CT cases where you've got lots of noise, you've got data that's incomplete in some way, so you're missing projections or parts of projections. Maybe you've got a non-standard geometry, you've scanned in a fancy setup, or maybe you've got a new kind of modality, so maybe a dynamic time-lapse type CT setup, or a spectral energy resolved setup, or something else. So these are the kind of data sets that we are particularly interested in handling. So CIL is highly modular. We supply a number of existing reconstruction algorithms, but also a lot of tools for you to prototype and construct your own algorithms for the particular problem you're working with. We've got a state-of-the-art optimization framework, nonlinear optimization framework, which is using a near mathematical syntax. So you can, if you know how to write optimization algorithms or write optimization problems, you can formulate things in a similar way here in core imaging library. Development has taken place in the, as I said, the CCPI, the Collaborative Computational Project in Tomographic Imaging, which is funded by the EPSFC. And the main link from where you can access CIL is the one at the bottom here. So I think Chris already showed you this diagram showing the main modules of CIL. I'll just talk a little bit about some of them. So we intend to provide a full pipeline of loading in data sets of different kinds. So our focus so far has not been on the medical side of things, but more on micro CT for material science purposes, so synchrotron data sets, and also lab CT cone beam setups. We've got our core elements to handle and represent our data and all of the geometry, which we call the framework. Then we've got lots of what we call processors to do different kinds of data corrections and conversions and so on, also to allow us to do slicing and masking of data, depending on what we need to do to the data. We've got a number of utilities, including to visualize data in different ways. We provide a number of demonstration data sets that you can play with, and also tools for simulating data, including adding different kinds of noise to your data. And one of the prime features is our optimization module, where we've got different algorithms, different fidelity functions and regularizers that you can use to construct different reconstruction methods. We also provide plugins for different tools. So for example, the regularization toolkit, another CCPI project, and many of you may know about the Astra toolbox or the Tigra CT toolbox that we've wrapped, and you can then use from within the framework here. Much of this is described in this paper down here. There's a preprint on archive here. I think the slides are available from HackMD or the website that you can go there. So I just wanted to show a number of things we've done using CIL in order to reconstruct non-standard data sets. So here's a case where we are looking at a cone beam setup, but we don't have a conventional setup because we've tilted the rotation axis. So it's a so-called laminography setup. We rotate around this tilted axis here and we record projections So here we have a nice Lego phantom we constructed. And in SIL, we can then represent this geometry, and we can carry out reconstruction with this, and we can play with a number of different algorithms. Here I have like a 2x2 study looking at different types of data fidelities and whether you include non-negativity and whether you do regularization. Here we've got some TV regularization, and you can see that in this vertical cross section here, you get some streak artifacts that are intrinsic to laminography, but with this regularized method, you're able to get rid of these artifacts. And this case study is in this paper down here. Another case where we are looking at time-lapse or dynamic CT, which is something we typically want to do quite fast to investigate some process that's happening. And depending on how many projections you get, you might be able to get a decent reconstruction with your standard FBP algorithm. But if you need to scan a lot faster, maybe you can only take 18 projections. Depending on the time scale your process is happening on, you might just get streaks. You do that. Now with SIL, you can play with different reconstruction algorithms and look at using information and adding regularization across the time domain, or in this case, we have some prior scans and some post scans that you can use as reference images and propagate structures into your reconstructions using these so-called directional TV. So this case study is in this other part 2 paper of describing the core imaging library. Another case is in hyperspectral neutron CT, where we've got an energy sensitive detector. So we measure, instead of one tomographic data set, we measure essentially thousands of tomographic data sets at different energies. And it's very similar to X-ray CT, just using neutrons. And again, we can see, we look at each of the energy channels and we reconstruct with our FBP algorithm. We get very, very noisy reconstructions. Whereas with SIL, we can play with different kinds of regularization. So we've got a method called TNV, total nuclear variation, which adds regularization across the energy domain, and another one here where we're enforcing TV in the spatial domain and a generalized form of TV in the spectral domain. And you can see you get much sharper edges. And also if we look at line profiles, you see we've reduced the noise quite substantially. It can pick up some of the small features that were not visible before, or if we look at single voxels for a particular material across the energy dimension, we see that we can reproduce basically the theoretical expected Bragg edges that are present in a particular sample quite well with these more sophisticated reconstruction methods. And this is described in this paper down here. So SIL actually is able to handle most linear inverse problems, I would say. So we supply a couple of different linear operators representing other inverse problems. So here's a case of a color image where we've added some noise and we've added some missing pixels, this black text here. And we can formulate that as an in-painting and denoising problem and use a L1 type data fidelity and a TGV regularizer, and we can see we're able to recover quite nicely the image here. And also, I think this case was already shown where we can use SIL to not do X-ray CT or basic image processing, but actually work with SIRF acquisition models for MRI in this case, and also incorporate a motion compensation model with some regularization using the core imaging library. So this was just to show a range of different things that we can do with the core imaging library. We'll start out with a few more basic things. So this week we will be looking at just getting up and running with SIL. So just loading some data in, manipulating it, and doing some basic filter back projection reconstruction, also doing a little bit of pre-processing data. Next week, we will turn more to optimization-based reconstruction. So we will have a go at specifying different optimization problems and running algorithms to solve the problems, and play with different regularizers and fidelities and constraints and so on. And now in the third week, we will go even more ambitious, and we will look at multi-channel reconstruction. So we will look at some of the dynamic and spectral cases I showed here, and also some multimodality or synergistic. Here are some resources. So the main website, as I mentioned, is at the top there. There's also a new documentation site, which is here, where you can look up some of the tools. And also I want to highlight these two papers that are about to appear, and the preprints are on archive, that are basically taking you through a number of the different things you can do with the core imaging library. Right, so my intention now was to actually run a small demo to show a bit more about SIL. So as Edo showed, I expect you see my browser now, right? Yes. Okay, so as Edo showed, we have the SIL demos folder in which we've got training material for this course, and we've got week 1 here. And we've got 6 notebooks that are intended for this week. Most of them are already, well, they will basically run, and you can step through them and read the text and see what's going on. Then we've got some more open-ended exercises at the end here, where you can try different data sets and play with different things. And also this number 0 notebook here is more of an overview and a deeper look into how we represent geometry and different kinds of geometries we can handle in SIL. Now, the one I wanted to walk you through was this, number 1 here. So in this one, we actually load in a real 3D lab micro CT data set, which is a cone beam data set of a walnut scanned on a size Versa instrument. So first of all, we need to import a few things. We need NumPy, and we need a number of different modules and tools here from SIL. So the first thing we want to do, and note that this data set is well, I've pre-run everything just to save a little bit of time here for the presentation. The data set that you need for most, or I think maybe even all of these notebooks, that's already on the STFC cloud. So here I can just specify the path to it, and I can then load it in. And that's done using this tool from SIL, which reads this particular data format. Now, once you've done that, you get this data here, and it turns out that that's this SIL acquisition data object. We can see that if we look at the type of it, we'll see it's printed. It's an acquisition data. And just like you could use, like I think Christoph mentioned, help, you can also print data, and you're informed about different things about the data set here. It's a 3-dimensional data set and the shape of it. And also we use what we call dimension labels to refer to the different dimensions of the data set here. So we can see that we've got 1601 projections labeled by angle, and they are all size 1024 by 1024 in the vertical and horizontal dimensions. So the data set contains more metadata or geometric information, and that's all held in this geometry field of the acquisition geometry here, which we can take a look at if we print it basically. So it'll show us it's a 3D cone beam data set with lots of details about how everything was positioned, the source and the rotation axis and detector positions and panel size and so on. So in addition to that, you can also use the tool which is called Show Geometry, which will read basically this info here and draw a nice picture for you to get a better idea visually of what's going on. So we see the cone here, and we see the reconstruction, the default reconstruction volume here, and the extent of the detector and coordinate systems and so on. This can be quite handy sometimes if you've got a rather complicated geometry to see what's going on. So, okay, we've taken a look at the geometry. We can now also, well, have a look at the data, and we have a tool here just to illustrate data. We can pick out from our data which slices we want, and note we can use our labels here. So in this case, we say, okay, I want the, without specifying whether this is index 0, 1, or 2 or whatever, we can say I want the angle number 800, and I would just want to look at that slice. So this is going to give us a projection to look at, which we can recognize is maybe a walnut. And we can see by looking at the background here that this is transmission data. We know it's been already pre-corrected for a number of things here, but this is basically the raw measurement here, just the transmission value. So the first thing we normally need to do to CT data in transmission format is we need to apply the Lambert-Beer, which is basically converted to absorption, which means we just take the negative log. We have a tool here, it's a processor, which will apply that to the data, just a negative log, and handle some outlier values for convenience here. Having done that, we can again take a look at the data. This time we look in another dimension, we look in the vertical dimension, pick out, this is the central slice basically, and here again we use the show 2D, and we see now a nice sinogram. So this is going to be this we could use and just reconstruct the central slice as a fan beam data set. Right, we are going to work with a full data set though, the full 3D volume. So here's a small thing that you need to do in CIL. You need to pay a little bit attention to what backend or what plugin you're using. Currently we support Astra and Tigre for doing forward projection and back projection of your data. And we need to make sure that the data is in the order that the particular backend is expecting. So here we can say, well, I need my data in the format expected by Astra, and the data is then going to be reordered like that. This means that our data is now ready, and we can start reconstructing it. We need to specify what sort of volume to reconstruct onto, how many voxels, and so on. Luckily, our data geometry has a way to create essentially the simplest setup, that's a simple scaling from your data set down to a volume here. So it'll just create a default volume for us to reconstruct onto. So if we don't have any particular needs, we just go with the default here. Having set up the image geometry here, and we have also our geometry for the acquisition, we can set up a FVP algorithm object to run on the GPU. This is a rather big data set, 1000 by 1000 by, what was it, 1600. So we need a GPU to be able to run it in reasonable time. Actually, it's the FDK algorithm, but we wrapped it as FVP. So we set up the algorithm here, and then we run it on the data. And when we've done that, we get a recon volume out here. This is a CIL image data. And again, we can use show 2D to take a look. And now we specify a couple of different slices here, a vertical one and a horizontal one. And we also make sure they have the same grayscale range so we can compare. And we see a nice horizontal slice here and then a nice vertical slice up here as well. And again, this is just to show you some of the things you can do CIL that might be useful in some of the data notebooks. If you're happy with this, you can export the data, save it to the disk. We've got some tools to do that. For example, you can export it as a TIFF stack. So we've got a TIFF writer here. Just commented it out to not run it every time because it takes a while and writes quite a lot of data to the disk, but you just remove the pound symbols and you're good. Right, so normally if we have a full nice data set like this, then really there's no point in going to more sophisticated reconstruction methods, because this is probably going to be perfectly fine for whatever kind of post-processing you want to do, segmentation or whatever you want to do. Now, sometimes that's not the case, and we can simulate if we had only 1/10 of the projections. So we can use one of the other CIL processors to do that. So it's called the slicer, and we will just use it here and reduce the number of projections in our data set by a factor of 10. So you need to specify here in a particular syntax for the slicer here. You start from 0, run to the end. It's kind of like NumPy slicing notation, and the step you take. Then you apply that to your data set and you get a reduced data set out here. We run again FBP on the reduced data now, again on the GPU, and we can see we get a reconstructed volume down here, which is not nearly as nice. We get lots of streaks and lots of artifacts showing up now over here. And this might be the starting point for having a go with other reconstruction methods to see if we do better when it's not just the FBP. Let's see, other than this first one here, we have a few more notebooks. We've got number 2 here, which is also using a real data set, a sandstone, a single slice of a parallel beam synchrotron data set. We've got it here. And again, I've run it here. You will load in some data and have a look at the different parts of your data and go through the different steps, look at the geometry, and have a play with the data, and in the end reconstruct. The next one, the pre-processing here, is looking a bit more at sometimes we do need to handle bad data in different ways, crop some of the data away or mask it in different ways. So it'll look a bit more at that. And the last one here, number 4, will look not just at FBP for the reconstruction method, but also some of the more basic iterative methods that we use in X-ray CT, the CGLS, and the SIRF algorithm that are available in SIL. I want to mention this last notebook here called Additional Exercises, Data and Resources. So in this one, so the other notebooks are fairly ready to go, and you can just sort of step through them, and maybe there are a few exercises, but most of the stuff will be working, and you can read the text, and hopefully you'll get a good idea of how to use SIL. So the intention here is that once you've done that, if you're up for it, you can then have a play with other data sets. So we provide a number of different data sets. Some are for Nikon micro CT machines, crystals and clay here, the Sophia beads, and also the one I showed, the Lego laminography data set. All of them are available. I believe they are on the STFC cloud. So if you use that setup, you have access to them already. If you're using virtual machine, you will have to go to these links and download the data sets. And there's also some other data sets here you can have a play with. I want to mention one thing: when you work with these data sets are real and fairly big 3D data sets. For just playing with reconstruction methods, it's sometimes nice to just work with a single slice. And so I want to highlight that once you've loaded in your data set, you can extract a single slice by, again, using the dimension labels and say, I want vertical slice number 27, for example. If it's a parallel beam data set, you can do that. And then you just get a 2D data set with the geometry updated to the 2D geometry. If you've got a cone beam data set, the only thing you can do is extract the central slice, which you do like this, and then you get a nice 2D fan beam or cone 2D geometry. And these data sets are all, I think, either Nikon data sets or size data sets, which you can read with these methods here. We've got a couple of ideas for things you can try out. Try different real data sets or simulate your own, play with reducing the amount of data you've got using some of the processes, and also some more open-ended ideas and playing with looking at some of the geometric artifacts. And the relevant notebooks are always mentioned here. You can go have a look at something related. And finally, once again, if you get stuck, which hopefully you won't too often, but when it happens, or if it happens, you can go to the documentation, have a look. You're also welcome to go have a look at the main repository where SIL lives, and the demos. The training material is all here in the demos. And then some papers. I mentioned these 2 papers, part 1 and part 2. They are on archive for now. I think next week they'll appear. And also here's one for hyperspectral X-ray CT, and here's one for the neutron case I talked about. I think maybe that was it. I wanted to just briefly, maybe in the interest of time, the SIL people can just quickly wave. So we've got Edo, you've already seen. We've got Gemma. We've also got Laura. I don't know, I can't see if people are. And we've got also Evangelos or Bagilis. And maybe also Evelina is joining us. I'm not sure, I've seen her today. I think that was it. Are there any questions at this time?
I think there is one question in the chat, if you
Okay.
can access it, or should I read it to you? So Giovanni is saying, if the geometry is described by projection matrices, is it possible to use the CIL reconstruction methods?
Oh, so we did have that at some point. I can't remember whether we still offer that. Maybe Vagelis remembers better. We do have a matrix operator, right?
Yes, but this will not work for large data. It probably will work in 2D because Astra can offer a sparse matrix to reproduce the matrix vector multiplication, but for 3D, no, because we do not have, Astra will not have this sparse array for 3D.
Okay, thank you, Vangelis. It might, I mean, depending on the setup you're looking at, it might be that it can work. So feel free to get in touch. We can maybe look at the case you're looking at. And yes, let's, so questions, I think it's better to go to HackMD because I think we'll close the Zoom session very soon. So HackMD, ask your questions and we'll keep an eye on the HackMD and try to answer questions there, and also pick out some of the questions to address on Wednesday in the session there.